Hi everybody and welcome back. In this lecture we will create the dataset class used to feed slices and corresponding segmentation masks to the network during training. The following libraries will be used to tackle this problem. Of course, pathlib for easy path handling, PyTorch to create the dataset class, NumPy for file loading and processing, emgorg to set the random seed, and last but not least, segmentation maps on image from emgorg.augmentables.segmaps to augment segmentation and slice in the same way. As usual, the imports are already provided. Alright, let's go. Our dataset needs to implement the following functionality. At first, we need to create a list containing the paths to all two-dimensional slices. To do so, we will use the glob function heavily. Next, we extract the corresponding label path for each slice path. We can now use those paths to load a slice and corresponding segmentation given an index. After loading the data, we need to apply data augmentation. Once more, please make sure that slice and mask are augmented identically. Last but not least, we return slice and mask. Alright, let's code the dataset. Above all, we define our dataset class. Let's call it cardiac dataset once more. As usual, it inherits from torch.utils.data.dataset. Within the dataset, we at first define the initialization function. It accepts, of course, self, the root directory, and our augmentation parameters. Initially, we create a class variable called all_files, which will store the paths to all slices by calling the function self.extract_files, which we define directly afterwards. Extract files only accepts the root path. After that, we assign the augmentation params to the corresponding class attribute. Alright, let's define extract files. In fact, we will make this function a static method because it never accesses any class attributes and thus there is no need for it to accept the self argument. We can now define the function, which therefore only accepts the root path. At first, we define an empty list called files, which will store the paths to all slices. Next, we loop over the generator returned by root.glob*, which yields the path to all subjects. Depending on whether we're in the train or validation split, we receive either 16 or 17 subjects or 4 respectively 5. We can now define the slice path by adding the string data to our subject path. Slice path now contains the full absolute path to the NumPy files of this particular subject. Last but not least, we use glob one more time to iterate over the resulting generator. Since we are only interested in NumPy files, we pass the search string *.npy. Within the loop, we simply append those paths to the files list, which we finally return. Alright, this method is done. We have now all paths to all individual slices. Next, we should define the helper function, which replaces the slice path by the segmentation path. We can simply copy this function from our pre-processing notebook. Note that as we stored the pre-processed slices in a directory called data, we have to replace images.tr by data. Additionally, we have to rename labels.tr to masks. Last but not least, we also convert this function to a static method. Alright, our helper function is complete. Now we can define the augmentation function. It accepts, of course, self and the corresponding slice and mask to augment. Before doing anything else, we use torch.randint to get a random integer between 0 and 100,000. As usual, we need to define the shape of the resulting tensor, 1 in our case, and directly call the item function afterwards to extract the corresponding scalar. This random integer is now passed to emgorg.seed to update the internal seed. This enables emgorg to produce random augmentations besides working with the PyTorch data loaders. After that, we override our passed mask object with the segmentation maps on image class, to which we have to pass at first the original mask and next its shape. Now emgorg is ready to augment mask and slice. Let us define two variables, sliceAug and maskAug, which store the result returned when calling our augmentation pipeline self.augment_params, to which we pass the slice as image and the segmentation map as segmentation maps. Last but not least, we need to extract the actual array from the augmented mask by calling maskAug.get_r. We can now return the augmented data. Perfect! The augmentation is complete. Before defining a getItem, let's quickly add the length function, which simply returns the length of our all files list. Now we are ready to define getItem, which accepts self plus the index idx. First, we use the passed index to extract a file path from self.all files. Subsequently, we use our helper function to get the corresponding mask path. Let us now use numpy.load to load the slice identified by the file path. Additionally, we directly convert it to float32 for training. After that, we load the matching segmentation mask. Next, we check whether an augmentation pipeline exists, and if so, we call our augmentation function self.augment to augment slice and mask. Finally, we return our data. Let us directly use numpy.expanddims to add the channel dimension. It accepts at first an array and next the dimension or channel we want it to add. 0 in our case. This spares us from calling unsqueeze all the time. We perform the same operation for the segmentation mask. Nice! Our dataset class is complete. In the next lecture, we are going to validate its functionality. Thanks!